Thanks. Hi, everyone. My name is Calvin. I'm a master's candidate of applied science at the Human Media Lab, Queen's University, Kingston, Ontario, Canada. I'm also the co-creator of the GridDrones system, which I'll be introducing you all to today. So this is GridDrones, which is composed of 15 small tangible drones, which we call bit drones on their own, arranged in a 3x5 configuration. But they're not just individual drones flying together in a formation. They're actually a rudimentary programmable matter display. So GridDrones is an effort towards the creation of the ultimate display, which I'm sure many of you are familiar with. It's a step beyond augmented and virtual reality all the way to a real reality. But the idea that physical computer interfaces would one day fully embody digital information is not new. In 1965, Ivan Sutherland first conceptualized such an interface. So the ultimate display would, of course, be a room within which the computer can control the existence of matter. A chair displayed in such a room would be good enough to sit in, handcuffs displayed in such a room would be confining, and a bullet displayed in such a room would be fatal. In 1991, Toffoli and Margolis coined the term programmable matter. Programmable matter could be assembled into clumps of arbitrary size and determined not by technological limits, but by economic ones. By their definition, programmable matter would consist of small, parallel, cellular automata nodes capable of geometrically shaping themselves in 3D space to create any kind of material structure. This concept of programmable matter was then further refined in Claytronics, in which catoms, or Claytronic atoms, form the material necessary to construct 3D tangible objects. The functional requirements for a Claytronic interface would be that each catom should be self-contained. That is, it should contain everything it needs for computation, locomotion, and actuation. No static power should be required for adhesion after attachment between catoms, and coordination should be done through local control. No external computation necessary. Catoms should also contain no moving parts. GridDrones builds on the functional requirements of these definitions. So bringing things back to the present, this of course is the MIT Media Lab's Inform Dynamic Shape Display, which allows for the physical rendering of 3D content and for tangible interaction with digital information. There is some exceptional current research in shape-changing displays and modular robotic interfaces that really toe the line between what could also be considered rudimentary programmable matter interfaces. So a prime example of a swarm robotic system is Harvard's Kilobots, which are capable of acting as a swarm robotic display, seen in this short video featuring the construction of a two-dimensional star. Zooids from Stanford's Shape Lab are similarly diminutive robots and are a prime example of a tangible robotic swarm interface. They are seen here interpolating a user's manual input to form a circle. Another example of a self-configuring robotic swarm is M-Blocks from MIT's CSAIL, capable of autonomously creating structures. These small cubes utilize the inertia from a rotary mass for propulsion and magnets to maintain physical connections between them. And most recently, here is a short clip of Intel's Drone 100 project, which quickly became Intel's Drone 500 project. Here it was deployed at a music festival earlier this year for live visualizations. And as you can see, it's a highly capable volumetric display composed of hundreds of individual drones. Which brings us to the rationale behind the creation of GridDrones. To start with, there are two approaches as to how we can interact with digital information in the future. Either we can augment ourselves, which is what we're currently doing for the most part, or we can alter reality, which is what we just saw several examples of. GridDrones aims to alter reality, but obviously this is a very difficult thing to do. From a programmable matter standpoint, none of the examples portrayed fulfill all of the criteria necessary. Swarms such as zooids are tangible but two-dimensional, while Intel's Drone 100, 500, and beyond are not tangible and are very sparse due to turbulence and thrust streams from nearby drones. With M-Blocks and Inform, we have 2.5D displays, which essentially means that 3D structures must be structurally stable because the individual elements are not self-supporting. In the design of GridDrones, we focused on the following features. GridDrones is naturally haptic due to being composed of self-propelled physical elements that can exert force, albeit not a large amount, but enough to provide a resistive force when they are being moved. All primary functions revolved around the tangibility of GridDrones, so most interactions are manual. Certain non-manual functions, such as parameter specification, was done using a smartphone app. Of course, being small, nimble drones, they are entirely self-levitating and self-powered. They are capable of 2.5D surface transformations, but because they are entirely mobile and self-supporting, they can also perform 3D transformations, such as rotation, translation, and scaling operations. GridDrones also has the ability to record tangible interactions as animations and replay them. In the implementation of GridDrones, it comprises of 5 main parts. So there are the input devices, the drones themselves, a UI layer for enacting different interaction scenarios, the flight controller, and the 3D positioning system. So these are the bit drones, which make up the GridDrone display as a whole. What you see on the right is the basic bit drone core, while on the left it's pictured securely fixed inside a lightweight carbon fiber and nylon cage. These cages were designed so that the drone could be tangibly manipulated and also double as a protective cage for the delicate components inside. Here's a slightly larger image that shows the main parts of the drone. So each has 4 brushed coreless motors with translucent propellers for propulsion, 4 RGB LEDs to illuminate the drone, a flight controller with integrated microcontrollers and IMUs, as well as Wi-Fi connectivity. And up at the top, you can see there are 5 infrared reflective markers with a unique pattern specific to each drone. These markers are triangulated by a Vicon motion capture system pictured here affixed to the ceiling, which provides position and orientation information of the drones. The left and right hands are recognized from a marker pattern affixed to a device worn by the user or by marker patterns affixed directly to the skin. This provides the system with information on when the user is touching or pointing. A simple smartphone app was created in order to control non-tangible aspects of GridDrones, such as specifying parameters or summoning tangible menus out of the drones themselves. The backbone of GridDrones is a 2.4 gigahertz Wi-Fi network. Ultimately, the system is mainly a centralized one with a flight controller computer running GridDrones OS connected directly to the network. This is a system diagrams of the GridDrone architecture. So first, the Vicon provides drone positions to the flight controller. The flight controller constructs control packets for each degree of freedom using multi-layered PID control, and then these control packets are then sent directly to the bit drones, which can also provide status messages as queried by the flight controller. The user then manually interacts with the drones or sets parameters using the smartphone app. This information passes through a UI layer, which runs the various interaction scenarios and specifies the necessary spatial arrangements of the drones in space. So as I highlighted earlier, the point of GridDrones is that it's a tangible display, which accepts both unimanual and bimanual input. There are 4 ways in which to group GridDrone elements using manual selection. Unimanually, a user can either select all, perform a contiguous or discontiguous selection, or perform a traditional lasso select. Bimanually, a user can also select a rectangular set of voxels between touch locations. So here, a user double taps a single bit drone to select all elements and group them. GridDrone behavior is then specified from the smartphone app. In this case, parameters were set in order to create a pyramid shape when a control point was dragged upwards. GridDrones also allows for arbitrary groupings within itself. Here, the user performs a discontiguous selection where only the corners of the grid are unimanually selected and grouped. A lasso select is also possible using a ray cast from the vector as indicated by the index finger. The lasso selection process is terminated by additional click with the thumb. 3D transformations are done entirely through bimanual interaction with the GridDrone display. With a bimanual interaction, the user can either rotate the GridDrones about all axes or translate along all axes in 3D. Beginning a bimanual interaction is as simple as the user reaching out and grabbing 2 drones. Moving them in space relative to each other allows for 3D rotations about all axes, and additionally, lateral translation is possible by simply moving the 2 drones together in the chosen direction of movement. So there are several examples that we have constructed and tested with the GridDrones, including 2.5D NURB surface modeling, tangible animation design, and flying Lego bricks. The most obvious application for GridDrones is in 3D modeling. The NURB surface application runs in the GridDrone UI layer, which allows the user to program a topological relationship between groups of bit drones. These relationships are programmed using the smartphone app, where a relationship can have a strength ranging between 0 to 100%. 100 would represent a hard material relationship, whereas 25% would represent more of a soft material relationship. Users can program multiple overlapping groups, allowing for complex behaviors to emerge. So here's the NURBS surface application in use. First, the user double taps to select all elements. Then a topological relationship is applied, roughly 50% in this case. By pushing and pulling the bit drones, which represent control points, deformations can be applied dynamically throughout the entire surface. Aforementioned 3D transformations can subsequently be applied in the form of 3D rotations and translations. Here, a raycast select is used and topological grid drone relationship set. Control points do not necessarily have to be individual drones, but can consist of a line of drones as selected through a raycast from the index finger. In this case, a raycast selection is used as a line control to construct an archway. It's also possible to animate these grid drones models and replay the animations. Using the grid, a user can program an animation by setting a topological relationship, beginning a recording, and then moving the bit drones. A recording menu is summoned from the smartphone to either record a new animation with the red button or play back a previously recorded one with the green button. The recording can be played back through the system, and the user can then move it around space using aforementioned 3D translation. Because manual interaction would conflict with the live animation, the model has to be grabbed via a closed fist gesture and then translation enacted through the extension of the index finger and then motion of the hand. So in February, we worked with LEGO to create a tool for creating and animating robotic structures based on bit drones, grid drones. Although the drones are pretty safe, we had to make sure such an experience was absolutely child-proof, both for the sake of the kids as well as the drones. We determined that separation from grid drones behind a window was the best option. To substitute tangible interaction with the drones themselves, we created an embodied controller to directly control them from behind the glass. Each embodied controller is connected to the grid drone's Wi-Fi network and has 2 integrated IMUs, 1 for each wing. They are also equipped with lights and an internal battery. The GridDrones UI layer uses the IMU data from each wing to determine the absolute orientation of each wing, as well as the relative orientation of the wings to each other. The body of the controller is constructed of a modified LEGO baseplate on which LEGO bricks can then be attached. A scanning table was also constructed with a USB camera and an Intel NUC PC running a custom OpenCV application to determine relative LEGO brick location as well as their color. Using an embodied controller, the user can scan a LEGO creation and then the system will do its best to recreate it. Once assembled, the system allows for full embodied control with direct mapping from the controller to the grid drones themselves. The bending of the controller wings will result in the relative bending of each wing in the flock, while rotating and tilting the controller will similarly result in a tilting and bending of the flock. We took the system to the 2018 LEGO World Expo in Copenhagen, where approximately 250 children used it. Each child responded positively to the exhibit without exception. Just last Thursday, we took the system to Madrid, where it appeared on a live show called El Hormiguero and was piloted by guest star Rick Astley. This demonstrated that the system is highly reliable, but it does have some issues. Which brings us to the limitations of grid drones. This was not an unfamiliar scene. So, namely, the battery life is relatively good for small drones at about 7 minutes, but it's not long enough for sustained use as a display. This is simply limited by modern battery technology, and there's not a lot we can do about it right now. The resolution of grid drones is limited by the cost of the drones, the physical volume and of the interaction space, as well as the size of the tracked volume as enabled by the Vicon motion capture system, which also contributes to the cost. Due to the proximity of the drones, they can't fly over top of one another, as they cannot stay aloft in the thrust streams of drones over top. This creates issues with true dense 3D models. Smaller drones would be better so that the density of the display could be higher, but the drones are completely custom designed by us, custom built, and also have to remain serviceable. So one way to circumvent the issues with battery life would be to dynamically replace drones as their batteries run out. If we can recharge drones at the same rate that they require replacement, then this would be a solution for longer use cases of the display. Wireless power transfer would negate the need for better batteries or dynamic replacement, but is pretty far off in terms of weight and power requirements for this project. Smaller drones will increase the display density of grid drones, which we're currently working on, and being able to hover over each other will allow for true 3D tangible construction. 3D group selection is only possible in a 2D grid at present, and alternate selection techniques will have to be explored for true 3D drone configurations. So we're also working on a physical mid-air connection, which will allow for a much denser display. Pictured here is just 4 drones, but we've done it with as much as 6, and we're hoping to scale that number up. But there's a lot of control systems issues that come along with flying larger flocks of connected drones. And that's it. Thank you.
All right, so let's line up for some questions. Dan is already over there. I knew it.
Hi, Daniel Ashbrook, University of Copenhagen. This is super cool. I really like the idea of being able to actually grab and physically manipulate these things. But something that I was thinking about is in the hand-wavy future, when you have 1,000 of these things, they start to get in the way of your body. And I'm curious then, how do you envision being able to manipulate a drone that is in the middle of the flock that you can't actually physically reach?
Absolutely. So that's kind of why we started exploring things like ray casting for selection. Obviously, there's a lot of work done with 3D selection in virtual reality. We find that there are issues with bringing this stuff from virtual reality studies to a physical thing, as you mentioned, but that definitely warrants much further research and studies with this system. With something like that, we might envision the user actually going into the display itself, doing interactions at a much smaller scale, and then taking a step back and maybe interacting gesturally with something of a much larger magnitude.
Cool, thank you.
All right.
Hi, I'm Yoon from Media Lab. I really like your project, but when I saw the 3D display in a 3D air, I saw that you're trying to display some image using LED color changing. But have you considered about to, instead of using a structure, because you're using a drone, that's why maybe you use a structure, a skeleton structure, but what would be another possible way to display an image on one module of the drone, or display a shape instead of one LED colors?
Well, to be honest, we haven't thought too much about that, just because what we're really focused on is the idea of each drone representing a CATM, representing a Claytronic atom. So we're more concerned with minimizing the overall size of the drones and increasing display density than actually trying to provide more contextually relevant information on one drone. So the focus, again, is really on managing all of the drones together instead of creating higher display resolution on the drone itself, which is kind of why we just stuck to one color, so that we would remain in that vein of research.
Okay, thank you.
All right, let's thank the speaker once more, and we're wrapping up the session. Just want to say